Welcome back. Today we're going to look at vectors. And you probably remember from Despicable Me that vectors have magnitude and direction. So we're talking about a directed line segment, and it has an initial point P. Let me just move it up so you can see, and a terminal point Q. And you can see that vector notation almost looks like a ray. So if we're going to describe vector V as a directed line segment, we often use lowercase bold letters to describe the vectors. And if we're describing or figuring out the magnitude, well, that's easy because that's also considered the length. So we use those two symbols that look like parallel lines down here and put the vector inside. So whenever you want to find the magnitude, we could just use the distance form because it is the length. All right, so let's consider these two vectors. Here we have vector V in orange, starting from 0, 0, and its terminal point is Q, 3, 1. And then we have vector U, it's the purple, with initial point 2, 2, and terminal point 5, 3. We want to prove that these vectors are equivalent, meaning they have the same direction and magnitude. So if we want to first figure out the magnitude, well, we just find the distance. So V is not too bad. It's just from 0. So if we're just going to multiply these, so it's just going to be 3 squared plus 1 squared, which is equal to the square root of 10. And then if I look at U, well, I just have to use some subtraction and make a little line here. So you can see it. All right, so subtract this. So we're going to have 5 minus 2 squared plus 3 minus 2 squared. And you can see really easily that that's going to be 3 squared plus 1 squared, which is also square root of 10, right? So perfect. They have the same distance, same length, same magnitude. That's what we're looking for. All right, the second thing we need to make sure we show is the direction. And looking at these values, we can actually use the slope to figure out the direction. So pretty easily for V, right? The slope of V would just be the rise over run. So that's just going to be 1 over 3. And then for U, we just do the same thing. So this is just going to be, it's a little bit more subtraction, but we have 3 minus 2 over 5 minus 2. So that's 1 over 3. So the same direction. Now, I'm just talking about the slope because that's what we've been using when we talk about a linear plane. When we have vectors, we often write the direction in component form. So let's go to component form. And component form is not too tough. I think that you guys will understand this pretty quickly. Okay, so component form, it really just has the change in the x and then the change in the y. So you can kind of see it has these little arrows at the end. All right, so if we're going to figure out a vector, we have vector with a component form of 1, 3. Well, it can be shown with different vectors. So these are all sort of a family of vectors. So you can see if you start with 0, 0, and then go to 1, 3, well, there's one vector. You can go from 0, negative 1, and then 1, 2, and then for the last one over here, which is down at the bottom of the blue, so you can actually start with 2, negative 3, and that coordinate is going to be 3, 0. That's going to be terminal. So again, you're adding 1 to the right, and then you're adding 3 to go up. All right, so in general, that component form describes a family of vectors. So it doesn't give you exactly its initial point and terminal point, but it tells you really the change. And then you can just use the distance formula to find the magnitude pretty easily. Okay, so now let's look at a vector here. So it's given initial point negative 2, 3, and terminal point 7, negative 7 and positive 9. Sorry. So I'm going to use this color here. So I drew it over here, and again, we're saying how far to the left? It's moving, right? So I'm going to just draw this here just so that we can see. But again, we're looking at the change in the x. So again, you subtract the initial point from the terminal point. So negative 7 minus a negative 2 is going to be plus 2. Okay, so it's going to go back. You can tell 5 units, right? It's going to go to the left. And then for the change in the y, well, if we're going to start with the terminal point minus the initial point. So again, we're saying what's that change? So it's going to go up 6. So in component form, it's going to be negative 5, comma 6. And that describes the change, right? The direction, right? And so we said the slope before, but it's going to give you the direction of that vector. And we like to use component forming. It's a little bit more clear, especially when we're talking about vectors, okay? All right, so let's go to some of the operations that we can do. So vector operations is most of these operations are algebraic. And so they're just written in a different form, but I think if we work with our basic algebraic expressions, we'll be able to simplify them and find them very easily. So again, here you have vector v. Well, you can cut vector v in half. So its magnitude would be half, right? So you can cut that in half, and that's just distributing that half. You can double vector v, so 2v. You can multiply by negative, meaning that it's going to be the opposite vector, right? So instead of going to the top right, it's going to the bottom left, right? It's going to be the opposite operation to kind of get back to where you started, right? And then you could also multiply by anything else. So this is negative 3/2, so it becomes it's 1.5 times that length and the opposite direction. So scalar multiples are treated just like distributions, and you just multiply everything. If it's twice the length, twice the change in the horizontal, you just multiply that by 2. Now addition, very similar. Okay, so we're working with finding the initial point and terminal point, but here we're adding and subtracting vectors. So that means that we have 2 vectors, and what we want to do is put them together to see what's the resultant. Okay, so if you can see, you have 2 vectors here, they're like just kind of scattered. So you can't really tell how to add them. So you have to put the, you can see that you're joining the initial point of the first vector with the terminal point of the second vector. So that here's u, and then we're adding vector v. So vector v is going to be here. And you can see when you're adding them, you end up making this parallelogram. So that's why we say this is the parallelogram law, because it is going to have 2 sides that are congruent and parallel, okay? And then that resultant is the diagonal. Now we can actually consider scalars and addition if we're going to find the difference. So the difference means that we're having to multiply by the negative of the vector. All right, so if we're going to add u plus negative v, that would be the same as u minus v. So we take that vector v, we multiply it by -1, and then we're going to add them. Okay, so that we now have I mean, you can still see you're kind of making a parallelogram in a way, but we like to, so we have this vector u, and then we have, here's the vector u, right? That's the ends up being the diagonal. And then you have minus the vector v, and you can see that this ends up being u plus negative v, or u minus v. All right, so looking at vector operations, you can use, like I said, all of the properties that are algebraic. You can use the associative property, here's the commutative property, the associative property, right? Identities, adding 0, right? When you're adding the opposite, the inverse property, additive inverse. You can use here's the associative with the multiplication. Here's some distribution, right? And then again, the identities. So 1 times u is u, 0 times u is 0. And then whenever we're having a scalar here, we're looking at that magnitude, you can multiply by the absolute value of that scalar, right? So any vector, if you're looking at something that's twice as big, 3 times as big, you can multiply by that scalar. Okay, so let's practice some operations with these vectors. So here we have vector u is 1, 2, and then vector v is 3, 1, and we're just going to add them. So I'm just going to show you here, we're adding the changes in the horizontal, And then we're adding the changes in the vertical. So u plus v, so we have 4, 3 in component form. Okay, and then u minus v, that means that we're going to have u, and then we're going to multiply that by the negative of v. All right, so I'm just going to put the negative v over here. So negative v, well, that's going to be negative 3, negative 1, right? The opposite, because it was 3, 1. And then when we're going to add those together, we'll have, let me just make a little line here so it's a little separated. All right, so we'll have 1 minus 3, and then 2 minus 1. So we have negative 2, 1. Just drawing a box so it's really clear. All right, in component form. All right, for the last one, 2u minus 3v. Now I'm going to just write this out just using distribution. All right, just so it could be, so we can see it. So it's 2 times the vector of u, which is 1, 2, and then plus, or sorry, minus 3, 3, 1. All right, so I'm just going to distribute these so that this is vector. If we double this, it's going to be 2, 4. And then I'm just going to make this a plus, negative 9, negative 3. And then we just add them together. So we have negative 7 and then 1. All right, so using just basic, almost algebraic operations with vectors. Okay, now the unit vector, very important. So whenever we have the unit vector, that's telling us that we're finding a vector with a length of 1. So if you're going to find the unit vector, well, first you have to find the length of the segment. So to find the length of the segment, that's the magnitude. So we find the magnitude, remember, with the distance formula. So if I'm going to find the magnitude of v, that's just going to be 3 squared plus 5 squared, which equals 9 plus 25, or square root of 34. So if that whole length is square root of 34, if I divide this vector by square root of 34, it'll give me the unit. So give me a vector with a magnitude of 1. So I can do two things. I can either just write this here. So I'm going to multiply, oh, I wrote unit twice. I'm going to multiply this vector by 1 over its magnitude, right? So we know that the magnitude is square root of 34, and I can't reduce that. So that's just going to be 1 over square root of 34 times the vector 3, 5. All right, we could, but usually you want to distribute it. So I'll write this as 3 over root 34 over 5 root 34. And then you can also rationalize it. So root 34 over 34, 5 root 34 over 34. Okay, so again, I'm going to actually use this value here to check. All right, so if we're going to figure out, does that work? Is that true? Well, I'm just going to write this on the side here. So remember, we could take that value and we could square both sides. So it would be 3 over root 34 squared plus 5 over 34 squared, which would just be 9 over 34 plus 25 over 34. And again, you get the 34 over 34, which equals 1. And the square root of 1 is just 1. So that is giving you the unit vector. The unit vector will have a magnitude of 1. All right, we just have it expressed in a couple ways here. We're going to talk a little bit more about that in another form. Okay, so for the next one, practice finding the unit vector. Pause the video and come back when you're ready. Okay, let's just check your answers. So to find the magnitude, you just use the distance formula. So 7 squared plus negative 3, 20 squared is 49 plus 9, which is square root of 58. You can't simplify that any further. So if we don't rationalize it, it'll be 7 over square root of 58, comma negative 3 over root 58, and then we can rationalize it as well. So the unit vector in a few different forms there. All right, so looking at the last part of this section, we're going to look at the standard unit vectors. So the standard unit vectors helps us to write the vectors in a linear combination. So, and I'm just going to backtrack. So just looking at component form, you notice that there's no variables in there. So the linear combination just helps us to write that. So you could identify the horizontal and vertical. So it's just a different way of writing it. So looking at a vector, right? First, if we're given the points are -2, 6, and the terminal point is -8, 3. The first part is we want to make sure we write that in component form. So in component form, it's just going to be -8 minus -2, which is +2, 3 minus 6. So this is -6, -3. Okay, so that's our vector u. And then if we want to write this as a linear combination, we're going to use I as the horizontal component and j as the vertical component. So here I'm going to write this as a linear combination. So it's just going to be -6i minus 3j. It's that easy. Okay. All right, so let's look at the next problem. Here we're given two vectors, u and v, written as linear combinations, and we're going to find 2u minus 3v. So this is actually very algebraic in a way. So if we're going to have 2u minus 3v, it's already in linear combination. So, and that's what we're going to write our final answer in. So I'll keep this in the same form. So it'll be 2 times I plus j. That's our vector u. And then our vector v will be 5i minus 3j. So we're actually just going to use algebra. Just distribute the 2, distribute the 3. This is -15i plus 9j. And then combine like terms. So you have -13i plus 11j. Right, just using basic rules of algebra. Now for 7, we're going to find a vector v, given that its magnitude is 6, and it is in the same direction as vector u. Now what we need to do is think about, okay, if we're going to make the magnitude 6, we should have the unit vector, so we can figure out, just multiply that by 6. So I'm going to find the unit vector of vector u. And remember, to find the unit vector, we're going to first find the distance. Well, it's -3, 3, so you could probably figure that out really quickly, but that's going to be square root of 9 plus 9. And remember, it's going to make a 45, 45, 90 triangle, so it's going to actually be 3 root 2, right? So it goes over to -3, up 3. That's going to be 45, 45. And so this would be 3 root 2. That'd be the distance or the magnitude. So I'm going to use this vector, right, and divide it by the magnitude. So that's 1 over 3 root 2, -3, 3. And when I write that again, I'm just going to write this with distributing. So this is going to be -3 over 3 root 2, 3 over 3 root 2. And you can kind of see this root 2. Remember, it's going to be root 2 over 2. We've got 45, 45. But I'm going to reduce this 3 here, just to make it a little bit easier. And then this will be the unit vector that I'm going to use. I'll leave it like this for a little while. Okay, so that's my unit vector. Well, we wanted to find a vector v that has a magnitude of 6. So vector v is going to be 6 times this vector, times that unit vector of u. So when I multiply that, we can just distribute. We'll have -6 over root 2, and I could read this as 6 root 2 over 2, and then 6 root 2 over 2, and you can see that this is going to reduce, which is good. So we have -3 root 2, 3 root 2. So our vector v will have a component form of negative 3 root 2, 3 root 2. And to walk through those steps again, remember we found the unit vector, because we said, oh, the magnitude of vector v is going to be 6 times that length. So we have to figure out what just a magnitude of 1 would be. So we found the unit vector of bu, and then multiplied that by 6 to find vector v. Well, I hope that was helpful, and I will see you all in class.